Hello students, welcome back. So in the previous video, we discussed the theoretical aspect of implementing a full adder using three different techniques. So in this video, we are going to talk about that how to implement using those three different methods, and we are going to compare the schematic diagram of all the three implementations and make some conclusions. So let us get started and implement using Xilinx Vivado. So students, I have made one design which is fa_if. That means I'm going to make a full adder using if statement. So these are my ports. A, B, C are inputs, sum and cout, these are the outputs. So one thing that I'm going to do here is define that my outputs are of the type register. This is one good habit, to define inputs as wire and outputs as register, that you should do. Now, when we have to write using if-else statement, first thing we have to mention is the sensitivity list. So we will say always at the rate, and inside the parentheses we are going to mention the sensitive input ports. Here all of them are sensitive. What is the meaning of sensitive? The ports on which the input cases will depend. So we will say A or B or C. That means if any one is changing. After always we will write begin, and a very good practice is you write end right now. Don't wait, because later you can forget it. So now within this always begin and end, we will write our if else condition. So we say if A equal to 0 and B equal 0 and C equal to 0. This is how we are comparing. If A is 0 and B is 0 and C is 0, then what should we do? Since we are going to define two statements, we are going to write begin and end. And then we say sum is equal to 0 and cout is also equal to 0. These statements, if you want, you can write like this also in one line, but since these are two statements, you have to mention begin and end. And now we are going to copy this and we are going to write the next statement. We are not going to write if, we will say else if. So 0 0 1. In that case, sum is going to be 1 and cout is going to be 0. So in the same manner, we are going to complete our code by writing all the 8 conditions. So here this is 0 0 1, then we mention 0 1 0 0 1 1, and here cout is going to be 1 and sum is equal to 0. So once we complete all the 8 cases, then we are going to save our code and check if anything is pending. If there is any error that is appearing, everything is fine. We make sure that this is our top module and we are going to generate the schematic for this. So the schematic is ready and we can see it is having a lot of multiplexers. If you zoom in, you are going to find that there are a lot of multiplexers here. The reason is, whenever we are writing if-else conditions, that decision can be made using multiplexer only. That means if this, select this, else select this. And we cannot manually cross-check it. Only with the test bench and waveform we can verify the functionality. Let us code the same full adder using the case statement now. So now I have defined my module fa_case. Again I have 3 inputs, 2 outputs, and outputs are registers. We are again going to say always at the rate A or B or C, begin and end, and then we say case, and this is important here. We are saying concatenation of A, B and C. That means these three input ports are concatenated as one single 3-bit number, and this is the order of concatenation. Now we can write our case statement based on this complete concatenated number. So we are going to write the first line as 3-bit 000. So this is my number, colon. Then we say begin. That means in this case, sum is equal to 0, semicolon, cout is equal to 0, semicolon, and end. So all those we can write in a single line also. So this way we are going to define all 8 cases. So here we have all the cases defined for 001, 010, 011, everything we have defined, and in the end we write end case. So that's it. We save it. If there is any error, it will be highlighted. If there is nothing, then it is good for us. And now let us see that what is the schematic. So this is our top module, and we check for the schematic now. So here what we have, we got a very simple schematic, but what is this? This is RTL ROM, read only memory. That means it is a memory element, and inside this memory element again we have some complex circuit which is not visible. So it is not an easy circuit. There is one ROM which is for cout calculation and one ROM for sum calculation. So it is again having a lot of elements involved. Now we are going to code the same full adder using the gate level modeling. So here we have our module full adder underscore gate. ABC are the inputs, sum and cout are the outputs. When we looked at the gate level diagram of the full adder, we had realized that there were 3 signals also. Let us have a look at the diagram again. So here we can see that the XOR of A and B is S1, AND of A and B is S2, and AND of S1 and C in is S3. These are the 3 signals that we need to define before we start writing the gate level code. So we are going to say wire S1, S2, S3 semicolon. So that's all. Then we say XOR, and we can mention X1, anything like that, D1, X1, anything of your choice. The output is S1, inputs are A, B, semicolon. Second, we have one AND gate. We can call it A1. The output is S2 and inputs are A and B. Next, we have another XOR gate. Where the output is sum and the inputs are S1 and C in. Then we have one AND gate which is output S3 and inputs are S1 and C. And finally we have one OR gate and the output is Cout and the inputs are S2 and S3. So that's all. The code, save it, and let us see that what is the schematic that we get. So here we got a very simple schematic, only 5 logic gates, the same which we have coded. So it is very area efficient. Now let us summarize all 3 schematics and compare that which one we should use. So students, we have seen the coding style using all the 3 different coding methods, and then we can summarize that when we used if-else, our schematic was very large. A lot of multiplexers were used because we had defined so many different if-else conditions. When it came to case level implementation using case statements, then we found that the schematic is made using read-only memory elements. Inside these two blocks, one is for sum, one is for cout, there will be again a lot of elements involved. They are not visible here, but this circuit is again going to take a lot of area. And finally, when we implemented using the gate level, we can see that we use only 5 gates. So this is the most optimal. It is going to be the fastest circuit and the most area efficient circuit also. So as we go ahead and code more complex circuit which require thousands of adders, now we can make a decision that which coding style should be adopted for using a full adder in the complex circuits. So students, now we know about the full adder. In our next video, we are going to make a 4-bit adder that is called 4-bit ripple carry adder. Keep learning. Thank you.